Hi guys, this is Jean-François Marie, Chief Solution Architect here at Kalray in France. Thank you for joining this session. We're going to talk about high-performance RoCE TCP solutions for end-to-end NVMe communication. We are very pleased to welcome you at SDC 20, and we are very lucky at Kalray to have 4 presentations this year. The first one will be a customer use case and will be presented by Jean-Baptiste Rio, one of our senior FAE. Rémi Goguet, our senior software architect, will go through how we build composable architectures. And myself, I'm very lucky to have 2 sessions. The first one you are just attending, and the second one at the same time in virtual conference will be about how we build composable architectures to build next generation data centers. So first about this session, what's the abstract? You all aware, I'm sure, that SSDs are getting more and more denser and have more and more performance. And it's really massive parallel protocol to take a benefit of those new devices. We are lucky to have a new protocol to address them internally with NVMe and other fabrics, Ethernet, fiber channel, and so on, so that we can exchange fast data. So this presentation will be about, we have NVMe, TCP, RoCE, and others, and I'm going to try to give you a bit of history and to try to compare those 2 protocols. What are the best use cases in order to take benefit of those 2 protocols and architectures? About myself, so as I told you, Jean-François, I've been 30 years in this industry, 25 years plus in the storage industry for data centers. Joining several companies as solution architect and its roles, such as Sun Microsystems, EMC, and NetApp for the latest 13 years, where I had different roles such as solution architect, managers, and director of product for EMEA. I'm very active in the community world. I've been active for SINIA for more than 10 years. I ran the French organization for 2 years, and I have a master's degree in electronics. But very interesting to run virtual events. You think that you cannot have 2 sessions in parallel, and I was very surprised to have that. And this year, the 2 sessions I'm going to present, this one about NVMe and the second one about composable architectures, actually are running at the same time. And this is kind of an ambiguity here. However, I think we're going to interact over Slack, and I would be very happy to answer all your questions around this virtual event and those 2 presentations. So let's get started with a bit of history. Let me show you some numbers. Make a guess. What are those numbers? Those numbers are disk RPMs. When I started in my career dealing with storage, we are selling fat, very large drives with small capacity, 3200 like RPM. Then within the 10 next years, I've seen the increase in terms of the size, reaching some terabytes, but the performance nearly was multiplied by 5 to reach 15K RPM. I suspect you'll recall those famous 146 15K RPM drives. So it was hundreds of gigabytes, not terabytes, no more than speed. And it was interesting to see that we were dealing a lot with those drives because they were failing and they were not that fast and not that fast enough for the demanding applications. Let's continue. What about those numbers? Do you recall them? Smaller ones, but another interesting history here. Those numbers are the max IOPS. So 300 IOPS were the max number of IOPS for 15,000 RPM SAS drives, right? 300 IOPS. And guess what happened? Those drives had tens of milliseconds of response time, while applications were demanding millisecond response time. I remember releasing SAP applications and where the best was around 2 to 3 milliseconds to get a satisfying installation. So for the many years, drives have been the DC bottleneck in terms of the architectures, in terms of the sizing, etc. And guess what? All the vendors were doing, they were putting in front of application massive cache. Suspect you remember EMC Symmetrics, Hitachi VSPs and others with those terabytes of cache just to hide HDD failures and HDD very high latency and very low speed. So what happened? Like 10 years ago, SSD started to come to market, and we see direct effects. At that time, I was NetApp, and I've seen that 15x type of difference in terms of IOPS. And what's happened? Suddenly, the backend drive started not to be the bottleneck, but it put a lot of pressure on the IO stack. Storage controllers had to rewrite completely the IO stack to take benefit of those SSDs. And the reason is very simple. HDD have a single line because they have a head, they have they are rotating devices, while SSDs are just electronics and they need parallelism, right? So at that time, we had that consideration around massive parallelisms for the first time. Immediate gains, low latency, very interesting to see that the drives were not the hotspots. Then we are in 2020. What are the latest figures? The latest first generation SAS SSDs are running around 30 kilo IOPS, while now NVMe or SAS SSD Gen 3 can sustain 500,000 IOPS, and the latest version of Gen 4 SSD, nearly all running over NVMe, are about 1.4 million IOPS. You see that magnitude of increase in terms of performance. It's a by 3,000, by 1,000 factors. So guess what? IO vendors, they have to do the job again, and they have to reconsider the IO stack completely, because no single server can sustain that load. So it's interesting that all the things are running across standards, and that's very important. So I told you that the need of an evolution from SCSI to NVMe was very important, because the change of the device, the way we address the device is completely different. And very happy at Kalray, because we are talking about massive parallelism, to say that we have a protocol to exchange data in a massive parallel way. So this is really a revolution for the IO stack. NVMe is addressing local devices, allowing servers to access faster the drives, decreasing the pressure or the amount of layers you have to go through to address the drive, moving from the SAS layers down to the NVMe layers. That's very interesting. However, the history again is interesting. Remember, mainframes, drive were internal, right? And then open systems. We tried to get the drives out. Then came NAS, then came fiber channel, so that we have a better consolidation way, better way of sharing and provisioning devices. And suddenly came HCI. Yeah, those things are too complex. We need to have all built in. But it's failing again, right? There are so many things which are not working properly that we have to consider another way. So coming those days, we have composable architectures, and the idea is to have those drives out, the servers in, and the weight of sharing, and the protocol of choice built around standards is NVMe of a fabric supporting many protocols. As we can see here, you have several ways, right? A PCI, NVMe over PCI to exchange internally, NVMe over fabric with different flavors, running with fiber channel, running with TCP and RoCE. So basically two techniques, right? I want to go super fast. I want to minimize the impact on my x86. I'm going to run RDMA type of techniques, and RoCE would be the best choice here. While, but you need specific equipment, right? If you want to go, using common Ethernet, then you're going to go choose TCP, good enough latency, good enough architectures, and then you can scale and share what you have. So it's very interesting to say that you can reuse your own infrastructure today. If we see what we have in terms of the best use cases, obviously the most demanding applications are still running over fiber channel. And fiber channel had to have NVMe to address those parallel devices. So FC NVMe is interesting when it comes to the enterprise category 0 type of applications. And the reason is very simple, because all enterprise customers have fiber channel switches. And it's very interesting that they just have to reuse the equipment, have the latest drivers to run NVMe on the top of it, and get a kind of a 30% improvement here. While the new applications, the new way of doing things, the new trends in terms of development, or in terms of AI, or in terms of the containers, etc., are driving the new standards adoption. And you see here two categories on the left-hand side and right-hand side. Either I need to go super fast, I need to have super low latency with a no SQL type of database, Cassandra type of application, etc. Then you're going to prefer running RoCE, while those big containers such as Hadoop for the data lakes, MongoDB database, just to get the data here, you may be okay just run and choose TCP. But the thing is important. There's no one size fits all, right? And perhaps it's difficult to choose one generic for all your applications if you have very demanding applications in terms of latency. However, choosing Ethernet as a common way is very interesting, because you can have both low latency with RoCE and kind of common things with TCP. You see here NVMe Express has a very strong roadmap in terms of the adoption of things, new technology, determinism, persistent memory, some better management things, and namespace type of architectures, etc. Have a look at NVMe Express website. Very strong roadmap to enhance NVMe and to enhance NVMe over Fabric and to have more features here. NVMe, as I told you, is really pushing boundaries. Let's see how and where. So I told you, remember those drives, those numbers, 300 IOPS, right? HDD. Pressure is really on drives. Storage nodes as well as compute nodes were demanding milliseconds type of response time. Remember those numbers are on SAP like 25 years ago. Usual protocols between compute node and storage node were fiber channel, SCSI, InfiniBand, some NAS here, while the backend from the storage node were only SCSI. So the pressure is on drive. And what happened at that time, as I told you, storage arrays, storage node had to implement cache techniques in order to hide those poor drives' latency. Then came SSDs. So here in a wide range, coming from, let's say, tens of Ks of IOPS to 500,000 IOPS, the latency around hundreds of microseconds. These are started to put pressure on the storage node. You may recall what happened, the rise of Pure Storage and others, taking the benefit of those new devices. I was net at that time, and we had to rewrite completely the I/O stack to take benefit of those new devices so that we could respond correctly to the I/O pressure coming from the applications. So pressure has moved up on the storage controllers, on the I/O stack, and what happened at that time, storage arrays had to reinvent I/O stacks to support SSDs. And what's happening today? We have even more powerful SSDs. As I told you, right, 1.5 million IOPS per SSD. So if you take 34 drives in an array, it's going to give you 40 million IOPS. The most powerful computer in one box is around 3 to 4 million IOPS. So there's no computer today that can sustain or can absorb 40 million IOPS. So you need to share. What's happening today? Those new devices are now putting pressure nonetheless on the on the storage node, but also on the compute nodes or the full stack. So that's very impressive, right? So yeah, we are talking here about devices with 10 of microseconds of response time, allowing application to take benefit of those, but there is a consideration of parallelism here. I remember when we started to test those SSDs with our old techniques, completely tuned for SCSI, it wasn't running well because we had single streams, not parallelized. We have to rethink how we were addressing those devices just for a benchmark purpose. It's exactly the same now for applications. So another thing, containers are very interesting for that matter because they are massively parallel. So you have millions of them running on the same infrastructure. So that's interesting how things are moving forward to absorb those IOs. And this is really the beginning of the story. So as I told you about this presentation, TCP, RoCE was the best choice. Obviously, you have a fiber channel element, but the discussion about RoCE and fiber channel is really the same, right? You need a dedicated architecture. You need dedicated switches. You cannot use your standard Ethernet switches, right? So comparing TCP and RoCE is kind of the same comparing TCP and fiber channel. So let's stick to that comparison here. So I bid for you this kind of summary so that you have all at once. So first, what type of driver, what type of HBA do I need to run those protocols? So the good news for TCP, just run your standard TCP, have the NVMe-oF driver, and it's going to go, right? While if you need RoCE, you want specific NIC supporting RDMA to run NVMe-oF RDMA RoCE, right? Both protocols suppose direct connect. You don't need switches. I told you that, yes, if you want to have a full infrastructure with switches, you're going to need specific features in your switch. Ethernet switch, you have RoCE like DCB protocols. However, you can have completely direct connect things, and this is what we are working at Kalray, is to avoid the use of switch, right? To decrease dramatically the price of the infrastructure in order to get benefits of those low latency networks and protocols. Obviously, if you're looking for latency, you have an application running on local nodes with NVMe SSD, and you would love to reproduce that same latency and performance. You will not go through using TCP. The path here is to consider RoCE, obviously, and you will see that the demanding applications are not embracing NVMe TCP, NVMe-oF TCP, sorry. They are embracing NVMe-oF RoCE. And the example I have in mind is VMware, for instance. The thing which is important is the pressure on the x86, right? If x86 is running the IO stack, TCP is very demanding in terms of the number of the megahertz and the x86 cycles, while RoCE, because it's memory-to-memory mapping, will put less pressure on x86. So if you look at your infrastructure and if you are x86 bound, it's interesting to consider those alternative protocols to decrease the pressure on the x86. If you have iSCSI infrastructure, right? iSCSI is okay, but it's not a matter of latency, not very good latency. The good news is running on TCP. So obviously, the replacement for iSCSI will be NVMe-oF TCP. You just use your standard NIC, you use your standard equipment, as I said. Just have the right driver, and right away you have far better performances. And to give you some figures, here at Kalray, we support multi-million IOPS just over TCP, while it's completely impossible running iSCSI. So it's very straightforward, and you may have a very important gain here just moving NVMe over TCP. InfiniBand, yeah, it's very expensive, quite commonly used for HPC, high demanding application in terms of bandwidth or very, very low latencies. Obviously, the replacement is not TCP. The past year is better to embrace RoCE, which has been big for that. And I told you, right, either you go the path to have a switch fabric, and maybe you will compare the price of the InfiniBand infrastructure versus the DCB infrastructure to run RoCE, and say, yeah, it's going to be the same. Yeah, maybe, right? Not sure, but how there are alternatives to go switchless, which is very interesting. And as I told you, a fiber channel alternative. I've been doing SAN for many years. Maybe you don't want to go that path, or you are in that path. And the good news is you have alternatives and choices. There's not just fiber channel to run things. Here, the protocol proposes things you can consider, so that you have really the choice for your infrastructures. So in summary, TCP for me is best in terms of capacity and general purpose applications. RoCE is really best for high performance and low latency purposes. So how do we build the future? How do we enable composable architectures? First, it's important to start with standards. And at Kalray, we rely on NVMe standards. One important thing for us, if you want to embrace composable architectures, is independency. You don't want to be locked in. You want the freedom of choice. So it's important for us to rely on a standard NVMe driver in order for you to choose the best OS you prefer in your data center. So, and embracing NVMe enables you to start with NVMe emulation, right? NVMe emulation allows us to have our card seen as an NVMe device. So any things behind the card will be seen as an NVMe resource. That's very interesting. You don't need complex setup. That's very straightforward. And this is really the first stone for independency. And very interesting to embrace the massive parallelism behind the card. So how Kalray smart card storage adapters are built, right? It starts with a processor. It's a homemade processor, 80 core. This is our third generation processor. Massively parallel architecture, non-blocking I/O architectures. Each core has a coprocessor to do fast computation, many DMAs, crypto accelerators to help you drive your security very efficiently. On the top of it, we have developed our own SDK, compilers, and so on and so forth, so that we can build and you can build your storage services. The name of this SDK is Access Core Storage, ACS, and it's really the cornerstone of storage services on the top of MPPA. What are we doing today? We are really offloading everything NVMe-oF, NVMe-oF TCP, NVMe-oF RoCE. We can run both in parallel. You can choose one or the other, or both at the same time. We are terminating TCP sessions. We are handling everything Ethernet. That's very, very, very interesting here. We have dedicated 1 gig Ethernet to do management. So you can have that as a standalone card within an x86 box, or you can use it through a BMC in a FBOF or GBOF if you prefer, to have like a storage device. Obviously, we are PCI compliant. We are PCI Gen 4 X16. And we are supporting NVMe emulation and peer-to-peer. Peer-to-peer is interesting. We are talking about I/O pressure. We are talking about offloading things. And as I told you before, x86 have a high pressure in terms of I/O. And what we are proposing here is to offload x86 I/Os, all those I/Os going to the drives. So using peer-to-peer technology, if you hook one of those cards in an x86 box, the x86 will not manage the drive anymore. We'll take over. We will manage the I/O to the drives. So the x86 running in the system will just handle the application. So it's a big, big, big gain for you, right? And perhaps 30, 50% of the x86 I/O, x86 use is just done for I/O. What if you have one card, one system, offloading that completely? And you will see with the specs, we have so many cores that we can run the fully loaded I/O NVMe-oF plus some extra services such as eraser coding, right? That's very interesting to combine those things. So the value here is you could be a companion of an x86 and offloading all the data services. So here, just a look at the card with some specs and all the features we have in the cards, some figures in terms of performance, and you will see that we are completely aligned to help you sustain the next generation SSD IOPS, right? And we're going to see an example just after the slide. We have, as I told you, a set of tools, a software development kit in order to add those services. And we have completely embraced the new way of handling I/O. We have separated control and management plane with data plane. So for us, as I told you, 80 cores organized in 5 clusters of 16 cores. One cluster of 16 cores will run control and management, and the other 4 clusters, 64 cores, will run the data plane. That's where NVMe-oF, TCP, and RoCE are sitting. This is where we can handle those million IOPS, right? 64 cores just to do I/O. As a reference architectures, we are working with our partner Wistron in Taiwan to build the next generation GBoF. So I'm using the terminology GBoF here because this is quite well known, but this is not exactly what we are doing here. A GBoF is just a bunch of flash, meaning that the array may be accessed using SCSI or TCP or RoCE, right? And this is what we're not building here. We are building an FBoF, right? You may not be used to that terminology, but and I think that's important to adopt it, because FBoF means fabric bunch of flash, meaning that your bunch of flash is addressed with a fabric. And this is what are RoCE and TCP. They are fabrics. So it's important to have this new terminology here. So you see the chassis, quite common chassis, 24 drives in the front, and a set of I/O module in the back. What is interesting here is for us this kind of architecture where you don't want to be in a blocking factor. We don't want the card to be in between your application and the SSDs in terms of slowing the performance. Let me give you some figures here. 24 drives, Gen 3, with nearly 500,000 IOPS per drive, will give you around 14 million IOPS. If you take the spec we have for the cards, 2 cards will handle like 8 million IOPS. So if you have 14 million IOPS coming from the drives and your cards only deliver 8 million IOPS, you are slowing down the drive. You do not take benefit of the drives. The good thing about this architecture, this is completely flexible. You really can choose 2 cards, 4 cards, 6 cards, depending the performance you want. Either you want more gigabyte per second, or either you want more IOPS per second. And it's important to see that if you have 6 cards, so you're going to get 20 plus million IOPS from the cards, you will not be card bound, you will be SSD bound. So you will take full benefit of your SSD performance. And we want that, right? And we are ready for Gen 4. So if you put Gen 4 drives, again with 6 cards, it's going to be interesting to see that you may be card bound. However, you will take more than 30 million IOPS type of performance, which is very, very interesting to see what will happen here with the next generation architectures. So watch out the LAN space. This bus will be out very soon. So what are we doing at Kalray? What are the 4 guidelines in terms of what the things we are doing? First, we are mad about performance, latency, IOPS, and bandwidth. We want you to take benefit of the next generation SSD, NVMe SSDs. And we want to make sure that we are helping you offloading your x86, right? those are causing I/O limitations. Those are the blocking factors those days. And with our solution, we believe that we can remove those bottlenecks. We are working on the cost, obviously, and we are fully behind composable architectures. One of the best example we demonstrate during our Remy Goguet presentation is how we can dismantle HCI, how we can disaggregate HCI. HCI is just a set of islands or silos of storage. We know how poor it is on how handling I/O. We know what are the problems in terms of the interconnect. And what we do here at Kalray is we can offload completely the x86, offload any data path from the interconnect so that you have no more bottleneck in terms of the I/O access. Our solutions are fully flexible, right? Fully programmable, as I told you, from a control and management plane to a data plane using SPDK. And obviously, we are future-proof, right? We leverage standards, NVMe standard, NVMe-oF standard, whether it's TCP or RoCE. We are compliant. We are making sure that we follow those standards, and we are running all the compliancy tests so that we follow those standards. So watch the space, watch Kalray, MPPA, K200, Wistron GBOF. Very interesting set of tools moving forward. You will see more from us. Thank you very much. Thank you for your time here. I hope you enjoyed the session. I hope we have a lot of exchange around Slack. Have a good day and see you next time. Bye-bye.